Let us now build on these ideas to develop a circuit element which is completely self-contained, that does not require the presence of some kind of an external magnetic field in order to drive the system. And this type of a device is known as an inductor. So what the inductor basically does is it is the same sort of situation as above, but we're going to make this self-contained. So there's not going to be any external magnetic field in our system. If that is the case, now what we are going to find is that the flux through our loop, this phi b, which we calculated before, is going to be N times the magnetic field going through our solenoid, just as we had before, at time t, times the area A. And tracking our signs very carefully, we know that if the current is in this direction that we're presuming for the present case, that the induced magnetic field from a current in this direction actually would be upward, and that upward direction is completely consistent with the area normal when, again, we agree to travel through the inductor here in the same direction as the current. So once again, in this case, we would find that in calculating the flux, we have that same factor of cosine of 0, which gives us a positive 1. Now, because we are ignoring any external magnetic fields and thinking only in terms of fields that are generated by the device itself, so this is a completely self-contained system, we know the magnitude of the field given by the standard solenoid formula. So the strength of the magnetic field here then is going to be nothing other than mu naught times the winding density, which is lowercase n, times the current at time t. So now we have a very nice expression here for the flux, and just to remind you, this came from the magnetic field B. I'd like to kind of get it into sort of a standard form. Notice I have the total winding number n as well as the winding density, number of turns per unit length. It'd be nice actually for us to use the just a single variable. So let's use lowercase n, which is the number of turns per unit length, times the length, and substitute that in for the total number of turns. And now we get a very nice expression for the total flux through this system. It's just going to have a factor of mu naught. We see it has, going in our factors now, taking our factors in order, there's a factor of n. Then there's a factor of L. I've already done the mu naught. There's another factor of n, so this will be n squared. I have the current, and then I have the area. And I'd like to write the area first so I can combine all of the things that characterize the inductor first, and then the external driving force, the current I of t, can go for me second. One kind of neat observation here, notice that we're going to make use of later. I'd like you to notice that I've got a fundamental constant, the permeability of space. I've got n squared, which tells me how tightly I've wound things on the solenoid. Then I have this interesting product, the length of the solenoid times the area of the solenoid. So this factor here is actually the volume of the solenoid. And that's kind of an interesting feature. That's one of those things that, make you go, I wonder what that's trying to tell me, that it's really involving volume. That comment aside, what we have now here is a quite general result I'd like you to take note of. So in general, the first thing we're noticing is that the flux through a coil like this, or an inductor, is actually just proportional to the current. And that makes a lot of sense physically. After all, the flux is going to be proportional to the magnetic field in the system. That certainly is reasonably expected. And also, magnetic field, generally speaking, is going to be proportional to the current flowing through the system. So it's natural that in general we expect the flux through a solenoid to be directly proportional to the current. That constant of proportionality has a standard name. It's called L is the symbol we use, and this is known as the inductance of the inductor. And in particular, this, if we want to be more precise, this is sometimes called the self-inductance. There's another concept where you have two coils talking to each other. That concept is known as mutual inductance. We won't be doing much with that in this course, but so we'll generally just call this the inductance. But I just want to note the more technical name for you. So in general, we can always write the flux through a solenoid like this as some inductance constant L times the current I at time t. And what we've just learned here in this case is how actually to calculate inductances. We've done really our first example of that. And we've calculated, in fact, the inductance for a simple solenoid. And in this case, we found this intriguing result that it's the permeability of space times the square of the winding density times then this factor that is really just the volume of the solenoid. It's somehow proportional to the volume. Very good. So, now that's the basic behavior of an inductor. What I'd like to do now is to think about how we would analyze a circuit involving just such a particular circuit element.